Hello, today we're going to be talking about counting systems, base 10 counting systems, base 2, base 8, and base 16. Why do we use a base 10 counting system? The answer is we have 10 fingers, and as a result it's very natural for us to work in a base 10 number system. But computers are very different. They work with on-off switches, and so their natural counting system is a base 2 counting system. Let's learn a little bit from the base 10 counting system. In the base 10 counting system, we have 10 one-digit numbers. Those are 0 through 9. The first two-digit number is the number 10. So in order to reach the 11th number, we have to expand beyond one column to two columns. This is a positional number system. And so the position represents a power of 10. So for example, 315,826 is represented by 3 times 10 to the 5th power plus 1 times 10 to the 4th power plus 5 times 10 to the 3rd power plus 8 times 10 squared plus 2 times 10 plus 6 times 10 to the 0, which is 1. When we add all those up, we get 315,826. And the positional number system is very convenient for us because we can work at each position and in a column-wise fashion. So we can add the columns or subtract the columns with borrows and carries. It's going to be the same in the base 2 system. Only in a base 2 system, instead of 10 one-digit numbers, we only have 2 one-digit numbers. To expand beyond one digit, we have to add a position. So let's look at an example. If we start counting in base 2, we start with 0. And then we move to 1. But here we run out of one-digit numbers. To move to two-digit numbers, we have to put a 1 in the next column and then a 0. So we can expand to 1, 0 and then 1, 1. But here we run out of two-digit numbers and we have to expand to three-digit numbers. And those are 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These numbers in base 2 correspond to the base 10 numbers that you see here. And we can easily convert back and forth between these. For example, the number 5. If we look at this, the number 5 in binary is represented by 1 times 10 squared, or I beg your pardon, 1 times 2 squared, 0 times 2 to the first, and 1 times 2 to the 0. If we add those up, 4 plus 0 plus 1, we get 5. That's our base 10 number. Let's look at some of the patterns that we see in the columns as we count in base 2. The first column alternates every other number. 0, 1, 0, 1, 0, 1. If we look at the next column, notice that they alternate in groupings of 2. So 0, 0 in the first one, then 1, 1, then 0, 0, then 1, 1. In the next column, we alternate in groups of 4. 4 zeros, which we drop, and then 4 ones. The next column, if we added it over, would alternate in groups of 8, and the next column in groups of 16. These are all powers of 2. Leading zeros, as I mentioned, can be dropped. However, it's often convenient to represent a fixed-width binary field. And so, a number like 0, 1, 1, 0, we can drop the leading 0 and just have 1, 1, 0. Okay? To convert from base 2 to base 10, we're going to use repeated division by 2, the base we're converting to, and look at the remainders when we're done. So, for example, to convert from 92 base 10 into binary, we would divide 92 by 2, and we would get 46 remainder 0. We would divide 46 by 2 and get 23 remainder 0. We would divide 23 by 2 and get 11 remainder 1. And so on all the way to the bottom where we divide 1 by 2 and get 0 remainder 1. And this is where the conversion stops. We then examine the remainders and enumerate them from the bottom to the top. And this gives us our final binary digits, which are 101, 1100. That's 92 in base 2. We can do the same thing converting from base 2 to base 10. Instead of using division, we'll use multiplication by a power of base 2. So again, we take this number and we write it in a column on the left. We then write a multiplication symbol and 2 to a power on the right. And so 0 times 2 to the 0 gives us 0, 0 times 2 to the first gives us 0, 1 times 2 squared gives us 4, 1 times 2 cubed gives us 8, and so on. And then we look at these numbers on the right-hand side and add them all up in base 10, and what we get is 92. So we can convert forward and backward from binary to base 10. Binary itself is pretty cumbersome. Looking at a long string of digits of ones and zeros is very difficult for the human eye to parse. So often what we'll do is we'll group those in sets of 3 or sets of 4. If we group a base 2 number in groups of 3, 2 to the 3rd power is 8, that's called octal. If we group them in sets of 4, 2 to the 4th power is 16, that's called hexadecimal. So here we have a table that looks at the first 8 numbers in base 2, 10, 8, and 16. Notice that base 10, 8, and 16 are all the same for the numbers 0 through 8. There's no changes here. But if we go beyond the number 7 in base 8, we run out of one-digit numbers and we have to add a position to the left. So for example, the number 8 in base 8 is 10. And we still count on forward. 10, 11, 12, 13, 14, 15, 16, 17. The next number after 17 in octal would be 20. Okay? In base 16, what we see is the numbers 0 through 9 are exactly the same, but we need more one-digit numbers beyond 9. And so we use A, B, C, D, E, and F to represent the quantities 10, 11, 12, 13, 14, and 15. And using these groupings, then, we can take any binary number, look up those groupings of 3 or 4 in these tables, and convert them to octal or hexadecimal. So, for example, when we have this long string of binary digits, we can convert that to octal and hexadecimal by grouping by sets of 3. So if we group by 3, we get the octal number 6745. Notice that all of those numbers are between 0 and 7. And when we group by 4, we get the number DE5. Again, these are numbers 0 through F. So, in summary, base 10 number systems are not universal. In fact, computers employ a binary number system internally. Number systems also use the power and the base to represent the positions. Converting from base 10 to another base involves dividing by the base and examining the remainder, and conversely, going from another base to base 10 involves multiplying by the base and then summing up the column. Octal and hexadecimal, finally, are convenience groupings of binary numbers.